I'd like to introduce Gordon Anderson and Joey Dean from our Canberra office. They are going to talk about lighting and energy management.
Thanks, Darren. All right, so I'm going to give you a free shot right now. The last time I was up on a stage, it was actually quite dark, and I actually don't remember much of the night, so I'm scared. Thanks very much. I'm Gordon Anderson. I am the sorry, what was that? What was that? Well, it worked 3 times. My name's Gordon Anderson. I am here with Joey Dean. We're actually going to start as the 2 Ronnies. So it's good morning from me.
And it's good morning from him.
I'll get that out of the road.
Look, while we do get started, if somebody does throw something at him and actually manages to hit him, there's extra benefits in it for everybody. Well, I'm sure you could get a start with a Major League Baseball team if you can actually hit him.
All right, enough of the fun. We're going to talk about lighting management, lighting and energy management. For those who have not used the Crestron DIN rail family of products, they have been around for probably 18 months, certainly in this country anyway, 18 months, 24 months. They are an easy way to extend the dollar spend of a customer on a project, very, very simply, whether it's in a resi job or whether it's in a commercial project such as a small boardroom. You just want to add 4 channels of lighting dimming or a little bit of switching. We've got some products that can help you and combine the system into one holistic project. So I'm going to hand it over to Joey, who's going to talk a little bit about the concepts, what types of loads that we can manage, and then I'll come back in soon with the DIN rail products.
Thanks, Gordo. For people that haven't met me before, I'm Joey Dean. Very new to the Crestron family as such, but not all that new to the way that the products work. The integrator that I have been working with in Canberra for the last 4 years, very much a leader in the way that the industry worked. Picked up a couple of national awards at the last Crestron conference for some integration work that they did. Fortunately, I had a great sort of introductory into the way that the Crestron products work. Hopefully now that we can take my product range, particularly with a lighting and electrical background, and also with some IT ranges, and bring it forward with the information that we're about to do. And if I...
Air gap error.
Good start, turn it on. Okay. What we're looking at is the purpose of the presentation we're going to do is a lot of the people that are in the room here are AV integrators and don't necessarily have an electrical background, and probably, quite frankly, really don't want to have an electrical background on where they're going to do. So what we want to do is we're going to have a reasonably quick sort of presentation on the different types of lighting loads that we've got, the different ways we can control it, and how we go about integrating that into a system so that you don't need to get electricians involved in the job, you don't have to get anybody else involved. You can start with the same family of products, you can start with the same tools and programming gear that we've got, and we can take it from a concept through design, through implementation, roll it in with the AV gear that we do, and use the standard range of software products that we use and we're familiar with to be able to come up with a complete solution for integrated building technologies, as Jason's just gone through and done with us. Before we can start doing anything with lighting, we need to know what the loads are going to be. So the different types of loads that we've got are switching loads, loads that don't need to be dimmed or can't be dimmed. We've got, in this country, we call it leading edge. For the Americans, that'd be forward fees. Newer technology, which is far easier and far friendlier on lamps in particular, is trailing edge. Then we go to fluorescent dimming, and there's different types of fluorescent dimming. We have analog, which started out as 1 to 10, probably more reference now as 0 to 10. We go to digital dimming, Primarily, there's two different types of digital dimming, DSI and DALI. We'll go into these in a little bit more depth as we go forward. And then we have a quick look at the way that LEDs work and how we can dim them. Right here. So as we go through, as I mentioned before, switching loads pretty easy. Turn the power on, turn the power off. Don't need to dim it, can't dim them. You can also use integrated switching now that if you want to do power management for amplifiers in a rack, you can turn the powers on and off in a rack. You don't need to go out to a third-party relay solution to be able to do it. Use a Crestron relay in the box, put a power outlet in the rack, wire it through the system, and you've got integral control of what you need to do in your power management. As we head forward with leading edge dimming, it was the first of the dimming technologies that came along. Relatively easy to make, has been around for many years, and for the most part will do almost anything that we need it to do. As low voltage transformers have moved from iron cord to electronic, there are preferences for using trailing edge because you get a smoother dimming curve out of it. The main issue that we get with leading edge dimmers is the way that the waves are cut. So if I just go past Gordo over here, the way that the leading edge dimmers work is the green wire that we've got up here is a normal sine wave, the 240 volt wave that we use. With a leading edge dimming, we keep it at 0 and then turn it on very quickly. Obviously, we're cutting away the first part of the wave. The power management that comes out of this, the power management that comes is that you work out the power that is encapsulated inside the wave is the load and the power that a source can see. By changing or regulating where this red line rises on the wave, you can control the power that a load sees. Therefore, you can control its intensity and also its power usage. Now, the main issue that comes, particularly when we start using switch mode power supplies, the first thing that's in a switch mode power supply is a capacitor, and it's used as a filter capacitor. The problem that we get is that when you go to turn it on, depending on where this first wave comes through, the capacitor charges very quickly, and initially it looks like a dead short, so it takes a lot of current when you first turn them on. The downside is that when you start turning it off, the capacitor acts like a battery in your supply and continues to try and supply voltage to the system. So you get voltage overruns, so instead of stopping at the wave where it normally would, you get overruns across the top. It generates noise onto the system, and particularly from an AV industry, whether it's video or audio that you're hearing, you can hear the noise being generated into the system. And the second thing is you can start blowing up transformers. New technology came through and we start looking at trailing edge dimming. The idea from a trailing edge dimming is that we get the same power management benefits of being able to control that the power that the load's going to see, but we let the voltage rise naturally with the wave as it's coming forward, but then we turn it off. Now, it doesn't matter how quickly we turn the power off to it because we just turn the current off and it'll drop instantly. The benefits on doing it this way is that you don't blow capacitors up, you don't generate noise. A lot of the inconsistencies that come from using leading edge dimming are solved. The downside of using trailing edge is that it costs a little bit more to make. So when you go out and you're trying to buy the pot dimmers that you still see that you'd control incandescent lights in your house, they'll be leading edge and they'll almost universally be a leading edge because they're cheaper to make. Now, when you start going to trailing edge, although it's far better on lamp quality, lamp life, it's dearer to make. So from a manufacturing point of view, you tend to find that people don't want to spend more to get the same load benefits and not necessarily looking at the longevity of the equipment that they're controlling. The third thing we come into is fluorescent lamps. With the government's push to ban incandescent lamp sales in Australia, which I believe has now actually come into effect, and the benefit or the requirements in design to have better power usage as part of the design of a space, the requirements to have the same light level output but lower power going in typically means that a lot of the work that we're going to do is going to be fluorescent. Whether you like the colour of the lamp that you've got with fluorescent fittings, it's something that we're going to have to deal with. The original types of fluorescent fittings you couldn't dim, iron cord, ran on mains frequency, flickered really badly. A lot of people got headaches from the mains frequency, 50 hertz running through the tubes, and you could see them flicker. The new technology on the ballast means that they now run at a much higher frequency. Typically, lamp frequencies are 25 kilohertz through the tube itself, which means that you can't see them flicker. They're quicker than the eye can see. It does give us a whole heap of benefits from being able to do it. You get this information called instant start. So rather than seeing a tube go blink, 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 and all of a sudden it jumps into gear, most of the electronic ballasts that you see nowadays, you turn the power on and they'll start straight away. No flash, no start. If they're a dimmable ballast, they tend to strike and then dim up, but that's more the way that the lamp is being controlled internally rather than the technology. So we get far easier starting, more reliable tube operations because we're not pulsing it with massive voltages, and we get smoother dimming. Everything's a tick in being able to do it this way. The downside of being able to do it is that the single ballast that we use now can control multiple tubes, but the design inside the ballasts themselves means that the tubes are wired in series. If a tube is loose or a tube fails, the multiple tubes inside the same fitting that are running off the same ballast don't work.